Welcome back. Today we're going to talk about indeterminate form and L'Hopital rule. This is the last section in chapter 6. What is the L'Hopital rule? Let's say we have two functions f and g, differentiable, and the derivative for the g function is, let's assume it is not zero. This is not equal to 0. I should have wrote, sorry about that. This is supposed to be the derivative is not 0. Why do we want to say that? Because we want to talk about the limit of f divided by g as x approaches to a. We want to answer this limit. This limit, if both numerator and denominator are well defined, then the limit is just dividing the limit of the numerator and denominator. But in some cases, we have the limit of the numerator turns out to be 0 as well as the denominator is 0. So if you remember, this was an indeterminate form because we could have simplified the function, then calculate the limit. Or sometimes you have infinity divided by infinity, which we don't know what this value is. So we need to simplify the limit, then calculate the limit after simplification. But there is a rule, an L'Hopital rule, that we can apply to these limits, and it doesn't require us to simplify. So what is this rule? Let me highlight the important part. Okay, let's assume the limit of the function f and the limit of the function g is 0. This means we're dealing with the first case of 0 over 0. If we have a limit to be 0 over 0, which is one of the indeterminate form, 0 over 0, then we can say, okay, the limit of the function f divided by g is going to be exactly the same as the limit of their derivative divided by each other. This is one of the perks of the L'Hopital rule. It turns out that the same thing holds if the limit is infinity divided by infinity, which means if the numerator and denominator both are infinity, then we can still use the fact that the limit of f divided by g is exactly the same as the limit of the derivatives divided by each other. One important thing is you notice that we didn't apply quotient rule. We just said L'Hopital rule says that the limits are equal in terms of the limit of the derivative of the numerator divided by the derivative of the denominator. There is a simple proof behind this. I don't want to go into the detail of it, but let's look at maybe the first case of 0 divided by 0. So let's assume that both the numerator and denominator is 0. Then if you're given limit f of x divided by g of x as x approaches to 0, you can assume this is the same as limit f of x minus f of a divided by g of x minus g of a as x approaches to a. Sorry, this is x approaching to a. Why can I say that? Because we assume that the limits at f, limits of f and g, they're both 0, which means these two terms are supposed to be 0. This is what our assumption was. So if you subtract 0 from anything, it doesn't make any difference. In this case, these two are equal to each other. This is a true statement. Then we can divide the numerator and denominator both by, write it as g of x minus g of a as x approaches to a. We can divide both numerator and denominator by x minus a. If I do divide the numerator by x minus a and denominator by the x minus a, I haven't changed anything about this equality. So it's still a true statement. But now if you look at the numerator, this was the definition for the derivative as limit x approaches to a. The same if you look at the denominator, this means the derivative at g, at x equal to a. So f prime of x divided by g prime of x as x approaches. And this is basically means that limit equals to this limit. And that is what the L'Hopital rule says. Okay. The same idea can be applied to infinities, but you have to write it in terms of infinity. You have to write it as 1 divided by infinity and turn it into 0, but it's the same idea. Okay, so let's use this to calculate the following examples. So let's see. Let's start with this. Limit sine x divided by 3x as x approaches to 0. First, check to see if it's an indeterminate form, meaning if we replace 0, what do we get? We get sine of 0. Maybe I should write it on the side. Here, let me change this color to blue. Okay, so if we replace 0, what we get is sine 0 divided by 3 times 0 means 0 divided by 0. That means we are dealing with the indeterminate form 0 over 0, which means in this case, I can apply the Hopital rule, LH. I'm using this LH just to mention that we're applying the Hopital rule, which means that you can say, okay, the derivative of the numerator, sine x derivative, divided by the derivative of the denominator, 3x derivative, as x approaches to 0. That's it. That's the Hopital rule. Now I'll simplify. What is the derivative of sine x? It is cosine x. The derivative of 3x is simply 3, as x approaches to 0. Now if we replace 0, what we get is cosine 0 divided by 3. Cosine 0 is 1, so 1/3. And what we found is basically the limit, which means the limit sine x divided by 3x is 1/3. We could have answered this already by the property that limit sine x divided by x is 1. So this would have been 1/3 simply. But using this Hopital rule makes it simpler, so we don't need to remember all those properties of the limit. Here's the next example. Limit e to the x minus 1 divided by sine x. What you need to check is always replace 0 or a, figure out if the limit is in indeterminate form. If this was 1/5, I wouldn't apply Hopital rule. But if it's something like 0 over 0 or infinity over infinity, then in that case, I have to apply the Hopital rule. So let's replace 0. What we get is e to the 0 minus 1 divided by sine of 0. Numerator is e to the 0, which is 1. 1 minus 1 would be 0. Denominator, sine 0 is 0. Therefore, it's an indeterminate form. I apply the Hopital rule. Means this equals to limit e to the x minus 1. You don't need to write this step over and over, but I'm going to write it a couple of times just to make sure you guys don't use the quotient. Because this, we don't apply the derivative to the whole thing. We apply the numerator and denominator separately. So now, limit e to the x minus 1 would be simply take the derivatives of each numerator and denominator separately. Derivative of e to the x minus 1 is e to the x. Derivative of sine x, cosine x. The x approaches to 0. Now replace 0. What we get is e to 0 divided by cosine of 0. E to 0 is 1, cosine of 0, 1, so 1. If this turns out, for example, to be 0 over 0, you again apply the Hopital rule. Okay, so now here 1 is the limit. Let's go on to the next example. Limit ln x divided by x squared minus 1 as x approaches 1. Now if we replace 0, what we get is ln 1 divided by, if we replace 1, you get ln 1 minus divided by x squared, which is supposed to be 1 squared minus 1. What we get is ln 1 is simply 0, 1 squared minus 1 is 0. So this is require Hopital rule. Okay, derivative of the numerator, 1 over x. Derivative of the denominator, 2x. As x approaches to 1. If you replace 1, 1 divided by 2. You see now this complicated limit, you could answer it in one step. So simply 1/2. Next one, what if the limit was infinity? We didn't do any example of the infinity. If you replace infinity, what you get is ln infinity divided by square root of infinity. Both numerator and denominators are infinity. Logarithmic function was increasing, square root of x is increasing as well, so therefore as x is increasing, the ln will be approaching infinity as well. So now this is an indeterminate form, then it means I can apply the Hopital rule. Again, first you have to make sure that it's in indeterminate form, then you can apply the Hopital rule. Derivative of ln x, 1 over x. derivative of square root of x, you should write in terms of x to the power 1/2. The derivative would be 1 divided by 2 square root of x as x approaches to infinity. If you replace infinity now, what you get is 1 divided by infinity divided by 1 over 2 square root of infinity. Means 0 divided by 0 again. This would be indeterminate form, which means I have to apply the L'Hopital rule again. But first, before you do that, if you can simplify it, try to simplify. In this case, we can simplify it. And 1 over x divided by 1 over 2 square root of x is, if you multiply both numerator and denominator, let me do that. If you multiply both numerator and denominator by an x, what you get is simply, why am I multiplying an x is just to get rid of this fraction. X times 1 over x is 1. X times 1 over 2 squared. Maybe let's multiply 2x just to get rid of this 2 as well. So we'll get 2. Sorry about that. 2 divided by the 2's will cancel out. X divided by square root of x is square root of x as x approaches to infinity. Now, if you replace infinity, what you get is 2 divided by infinity. And what is 2 divided by infinity? As the denominator is increasing, 2 divided by a huge number, almost 0. So therefore, the limit turns out to be 0. Okay, so simplification helped us, and we didn't need that L'Hopital rule again. And it turns out if you continue taking the L'Hopital in this case, it's not going to help. The denominators are going to get larger and larger, so simplification is required. Okay, these are the simple cases of indeterminate. There are other types of indeterminate forms. One is the product. It means if you're calculating a limit, the limit f times g as x approaches to some constant a, and by replacing a, you'll end up with maybe the function f goes to 0, g goes to infinity, or vice versa, g goes to 0 and f goes to infinity. In these cases, this is an indeterminate form because 0 times infinity doesn't mean it's going to be 0. Maybe infinity is larger compared to 0, something like x times 1 over x squared. This may go to 0 faster than this one goes to infinity. So the product would be 0 in that case. Or sometimes you have x times 1 over x. In that case, the product would be approaching 1. So this is another indeterminate form. In this case, since it's multiplication and our only rule for L'Hopital rule is to apply it to the fraction, what we can do is we can write this f times g in terms of a fraction. How we do that? We can move one of these terms into the denominator. If I have g, I have f times g. I can write it as f divided by g to the power negative 1. This is g to the power 1. G to the power negative 1 means 1 over g. So you can write this f times 1 over g, f divided by 1 over g. This is what you can do. Now that you put it in the fraction form, you can apply the L'Hopital rule. And in that case means take the derivative of the numerator, divide by the derivative of the denominator, 1 over g derivative. Okay, this is all in limit sense. Limit the x approaches to a everywhere. Another case of indeterminate form is when you have subtraction. That's only for the infinities. If it was numbers, you can simply subtract. If it was 0 minus 0, the result would be 0. But if you have infinity minus infinity, it doesn't tell you which infinity is larger. So in these cases, normally, if they have common factors, you try to factor out between f and g. If factoring is not possible and you can combine the two functions, then you would do that and turn it into a division if possible. So depending on the question, you should either turn it into a product or division. I'll show you an example and we apply these rules. So let's see. Change this color back to red, sorry. Okay, so let's do these examples. Let's say we have limit x times ln x as x approaches to 0. If you remember, the domain of ln x is all positive number. That's why we have 0 from right side approach. So now if you Yeah, replace 0. What we have is 0 times ln 0 is positive infinity. Sorry, negative infinity, not positive. So what we have is product of 0 and infinity. Is if you multiply x times ln x and x approaches to 0 from right side. This would be 0 times ln 0 on the right side is infinity, negative infinity. So this is an indeterminate form. What we can do is we can write this as limit. Ask yourself which one is easier to deal with. Having ln x in the numerator and instead of x as a multiplication, 1 over x in the denominator, or having x divided by 1 over ln x. Which one seems to be easier? Sorry, x approaching to 0. Right side. Whichever looks easier to take the derivative, maybe you should pick that one. In this case, to me this format looks easier. And it's not always about which one looks easier. Sometimes it's possible to simplify it if you pick ln x to be in the numerator, sometimes in the denominator. So in this case, I'll pick the numerator. And if we go on next step, means take the derivative, ln x, divide by the derivative of 1 over x, as x approaches to 0 from right. In this case, what we have got is now the derivative of the numerator would be simply 1 over x. Derivative of the denominator, 1 over x derivative, you should apply quotient rule or write this x to negative 1. Would be negative 1 over x squared as x approaches to 0 from right. You can simplify this as limit, multiply both numerator and denominator by x squared. So what you get is x squared times 1 over x is x. X squared times negative 1 over x squared is negative 1. As x approaches to 0 from right side. Now if you replace 0, what you get is 0 divided by negative 1. Just simply 0. So we found out the product of x times ln x as x approaches to 0 is simply 0. Not always 0, so do not expect that this result is always 0. Another example is limit x times e to the x as x approaches to infinity, negative infinity. In this case, what you get is negative infinity. You replace negative infinity times e to the negative infinity, which means negative infinity times e to the negative infinity. If the exponent is getting smaller and smaller, remember exponential, this was the form of e to the x. As x approaches to negative infinity, the y value is approaching 0. So this is times 0. So this is an indeterminate form. This was e to the x, by the way. As we go into our negative infinity, the y value is getting closer and closer to 0. So what we have is, I can try this to write this in terms of exponential. In terms of either x divided by e to the x, x divided by 1 over e to the x, or I can write this e to the x divided by 1 over x. Ask yourself which one looks easier. It turns out this one looks easier, but it's not true that that looks easier, because you can rewrite this. You can rewrite this one as limit x divided by 1 over e to the x is simply e to the negative x as x approaches to negative infinity. Now you compare this with the other format, you'll notice this is much easier. So now I can apply the Hopital rule. By the way, I forgot to write the Hopital rule here. LH. It's not required, but it's better to write it so you show that what you're doing. Okay, take the derivatives. Derivative of the numerator is simply 1. Derivative of the denominator, e to the negative x derivative is e to the negative x multiplied by the derivative of the exponent, which is simply negative 1, as x approaches to negative infinity. So now if you replace infinity, you'll get 1 divided by e to the negative infinity multiplied by negative 1. That is 1 divided by e to the positive infinity times negative 1, which means negative. And this is simply 1 divided by negative infinity, which is equal to 0. 1 divided by a small negative number, sorry, a large negative number, is 0. Again, it doesn't mean that always you will get 0. It turns out these examples that I picked were not maybe best choice to see a different value. But if you apply the Hopital rule, in other case, you write it the other way, e to the x divided by 1 over x. It turns out this is not a good option because the denominator will give you x squared and then you cannot get rid of that x squared. The derivative of e to the x will stay as it. My mentality is if you're dealing with, here is maybe one idea. This is not always true, but maybe I should write this as a note. If you're dealing with indeterminate form of 0 times infinity, if the determinant form is in that case, and it involves ln x or e to the x, move, e to the x to the denominator in most cases. And if it involves ln x, move ln x, keep ln x in the numerator. Again, this is not always true, but in most cases, this is how you can simplify, how you can apply the Hopital rule, and turns out to be a best choice. Not always true, but most time this is the case. How about limit secant minus tangent as x approaches to pi half from left side? So let's figure out what is that. It would be secant pi half minus tangent pi half from left side. Maybe I should mention. If you don't remember the graphs, it's okay. So here, maybe secant is 1 divided by cosine. So it would be 1 over cosine pi half minus sine pi half divided by tangent pi, divided by cosine pi half. Okay, you should know the graph of sine and cosine, or values of sine and cosine better than tangent and secant. Here's pi half, and this is sine function. And if you look at the cosine, cosine looks like this at pi half. I stop at pi half because we are approaching from left side, so I only care about this value. So if we're approaching from left side, the 0, y value approaches to 0, but it approaches from right, from above. So the y value would be positive, which means this is a positive 0, as well as this one is a positive 0. Sine turns out to be 1. This is 1. So what you have is kind of 1 divided by 0, which is an infinity, minus another infinity, which is an indeterminate form. So what we can do is we can try to apply either one of the Hopital rules or try to simplify it. But the Hopital rules apply to fractions. So somehow we try to turn this into a fraction. And I've already given you the idea that to write in terms of sine and cosine. This would be 1 divided by cosine x minus sine divided by cosine x. As x approaches to pi half from left. And then you cannot deal with this negative sign in between. You have to turn it into one fraction, then you can apply the Hopital rule. So I can write it as 1 minus sine x divided by cosine x, as x approaches to pi half from left. Now if you replace pi half in there, what you would get is 1 minus sine pi half divided by pi half cosine pi half. In this case, you will deal with 0 over 0, which means now you can apply the Hopital rule. So if we apply the Hopital rule, what do we get is this equals limit the derivative of the numerator Divide by the derivative of denominator. Derivative of 1 minus sine x is negative cosine x. Derivative of cosine x is negative sine x. Now if you replace pi half, what do we get is negative 0 divided by negative 1. Turns out to be 0. So this limit sine x minus tangent x turns out to be 0. Again, it's not possible to calculate infinity minus infinity and say this is 0. Not always that's the case. Something like limit x squared minus x as x approaches to infinity. This would be infinity squared minus infinity, and you say infinity squared is larger, but that's not the case. You shouldn't always do that. What you can do is you can factor x, and you would have x times x minus 1 as x approaches to infinity. Now you can replace infinity and say, okay, this is infinity times infinity minus 1. This is infinity times infinity minus 1 is still infinity. Therefore, the result is infinity. This is how you would deal. So either you will turn it into a product or you turn it into a fraction. And if required, you apply the Hopital. Okay. This was kind of those two cases that I mentioned, product or the difference. Another form of the indeterminate form is through powers. Some powers are well defined, something like 0 to the power 1, this is always 0. But 0 to the power 0, that's an indeterminate form. Infinity to the power 0, that's another indeterminate form. Means, is this number large enough that the power 0 turns out to be 1, or is it a different number? So this is infinity to the power 0. Sorry. Infinity to the power 0 is indeterminate, and 1 to the power infinity is indeterminate as well. This is in limit sense. Why is 1 to the power infinity is indeterminate? Because sometimes you have something like 0.9 to the power infinity. And it turns out this means 0.9 multiplied by itself over and over times 0.9 times 0.9 and so on. And the more you multiply a number between 0 and 1 by itself, the smaller this will get, and it will approach 0. On the other side, if this number was something like 1.1 to the power infinity, then 1.1 times 1.1 times and so on, this would be infinity. So there is a huge gap between approaching from left side of 1 or right side of 1. So this is 1 to the power infinity, kind of indeterminate in the sense that we have to figure out which direction are we approaching. Mostly, the idea is the same. So what is the idea? The idea is to use that ln trick that we learned to deal with the x to the power x derivative, or x to the power ln x derivative. So let's say we have y equals f to the power g. We have this function, f to the power g, which means both numerator, both the function and the exponent are both variables, the base and the exponent. Sorry about this. I picked the wrong one. Okay, maybe let's choose different color. Here, let me highlight this. The base and the exponent, they're both functions. And let's assume this limit of this function, f to the power g, approaches to different one of these indeterminate cases. In that case, what we can do is we can take an ln from both sides. What you would get is ln y equals ln f to the power g, but we can drag down the exponent and write it as ln y equals g times ln f. This was by the property of the logarithmic function. And then if you take the limit at this moment, what you would get is you would figure out what is this value, because even if it's indeterminate, we can apply we can write in terms of fraction, apply the Hopital and figure out what is the g times ln f limit. Then to get rid of the ln, we basically raise both sides to the power e when we find out what is e to the power g ln f. I'll show you through an example, and what I would use is if given this function, I will write it in this format because they're equivalent to each other, and then take the limit of the exponent, and e to that power would be our answer. So here's an example. 1 plus sine 4x to the power cotangent x. So what am I assuming? I assume that y equals 1 plus 4x to the power cotangent x. First, you need to check if this is an indeterminate form, because if it's not an indeterminate form, then we already have the answer. So if you replace 0 from right side, what you get is 1 plus 4 sine 0, 1 plus 4 times 0 to the power cotangent 0, which would be 1 plus 0, which is 0, cotangent 0 from right side to infinity. So 1 to the power infinity, one of the indeterminate form. So therefore, now I can apply this trick, write this limit as limit e to the power. This is our f function, and here's our g function. So I can write it as g function, which is cotangent x, multiplied by 1 plus, ln 1 plus sine 4x as x approaches to 0 from right side. What do I need to figure out? I need to figure out what is this limit. If I figure out that value, then the answer would be e to the power that. So I'm going to focus on the limit of x approaching to 0 from right side of cotangent x multiplied by ln 1 plus sine 4x. And we already know this is 0 times infinity. This is 0 times infinity because this was 1, ln of 1 would be 0, and cotangent of 0 is infinity. So you will get infinity times 0, which is an indeterminate form. So we have to deal with this as if we're using Hopital rule. But before we do that, we have to write in terms of fraction. So I'm going to do that. And as I mentioned above, if you're dealing with ln, keep the ln in the numerator. So ln 1 plus sine 4x divided by 1 over cotangent x. Here's the good part. What is 1 divided by cotangent x? 1 divided by cotangent x is simply tangent x. So I can write the limit as limit x approaching to 0 from right side of, of ln 1 plus sine 4x divided by tangent x. Now taking the derivative would be easy, so I'm going to take the Hopital rule. We'll get limit. Don't forget the limit part. Derivative of ln 1 divided by sine 4 plus sine 1 plus sine 4x is 1 divided by sine 4x. 1 divided by 1 plus sine 4x multiplied by the derivative of 1 plus sine 4x, which is 4 cosine 4x. We applied chain rule. Don't forget that. Derivative of tangent x is secant squared x. I'm expecting that you guys already know how to take the derivative properly. You have to apply chain rule to this. Then when you're dealing with the derivative of sine 4x, you apply chain rule again to that. Okay. Before we calculate the value, I will try to simplify it. If you replace, if you write this in terms of limit, this is limit. Secant squared is 1 over cosine squared. I can move it to numerator and say, okay, this is limit 4 cosine to the, cosine 4x times cosine squared x. Instead of secant squared, I write 1 over cosine squared and multiply both numerator and denominator by cosine squared to get rid of the secant squared. And 1 plus sine 4x would be still in the denominator as x approaches to 0 from right side. He didn't require to write this, but I wanted to show you that simplification is the best choice sometimes. Now if you replace 0, what you get is 4 times cosine 0, which is 1, multiplied by cosine 0 again, 1, divided by 1 plus sine 0, which is 0. So what you get is simply 4. Is it our answer? Not really, because what we found at the moment is not e to that power. We only found the exponent. This is only the limit of the exponent. So what is our answer? The answer would be e to the power 4, because the e is still there. We only found the limit of the exponent, so we have e to the power 4 as our answer. It may be a bit complicated, so here's another example. Limit x to the power ln 2 divided by 1 plus ln x. First, make sure that this limit is an indeterminate form. So I will check if I replace infinity. What do I get is infinity to the power ln 2 divided by 1 plus infinity, which is infinity to the power 0. So therefore, this is an indeterminate form. ln 2 is a number. 1 divided by that number divided by infinity is a small number, so approaching 0. That's why we have e to the power, we have infinity to the power 0. So what do we do? Again, we write this as limit x approaches to infinity. This was our f function. This is the g function. So we write it as e to the power g function ln 2 divided by 1 plus ln x multiplied by the f function ln of the f function ln x. Again, I'll find the limit of the exponent first because the base is a constant, so the result would be e to the power of whatever we find as a limit. The limit of ln 2 divided by 1 plus ln x times ln x as x approaches to infinity. So now what we have is, if you replace infinity, what you get is infinity divided by infinity. So we require Hopital rule. Apply the Hopital rule. ln 2, you can write this as one fraction as well. Maybe that would have been better in the next step. So let me erase the L. So let's write this as limit ln 2 times ln x divided by 1 plus ln as x approaches to infinity. ln 2 is a constant. Don't forget that. This is a constant, so if you're applying the derivative, it's not going to go anywhere. So you will get limit ln 2 multiplied by the derivative of ln x, which is 1 over x, divided by 1 plus ln x derivative, 1 over x. X approaches to infinity. These two can cancel out. The answer would be simply ln 2. So what we get is e to the power ln 2. And what is e to the power ln 2? E and ln are inverse of each other. So simply 2. And we figure out that the limit is 2 for this function. It's not obvious that the limit is 2, but if you go through the process carefully, you'll notice that the limit will be 2. Okay, so this last topic, this last and indeterminate form is the most complicated one. And most of the time, you write it as this. And you just need to find out the limit of the exponent. And e to that power, e to that result, whatever you find is the limit value. Okay, one important thing that I haven't mentioned is, I didn't mention this because we've already talked about it. I didn't do an example of it, but I mentioned this limit, let's say x plus 2 divided by 5x as x approaches to 1. If you replace 1, what you get is 3 divided by 5. it doesn't require Hopital rule. There is no Hopital rule needed because it's not an indeterminate form. You can only use Hopital rule. This is only possible if you have the indeterminate form. If you're dealing with 0 over 0, infinity over infinity, it could be plus or minus. If you're dealing with 0 times infinity, or if you're dealing with, let's say, infinity minus infinity, or what else? There's 0 to the power 0, infinity to the power 0, or the last one was 1 to the power infinity. In these cases, you apply Hopital rule, but you have to write in terms of a fraction first, then you apply the Hopital rule. These cases are the ones that sometimes require Hopital rule, sometimes it's simple and it doesn't require Hopital rule. Okay, so now this would be the end of chapter 6. I'm going to stop here. Next time we will start on chapter 7.